already have 5 weeks course earlier before this is FRI. We have done some learning before that, and so this week is CircleStarks. And there will be some paper reading and sharing and discussion. So I think later we'll move on to the upstairs. There is a small room, and there will be some open sharing this week. And also we welcome all of you to join us. Oh.
Hello everyone, my name is Pan. As Harry said, this talk, yesterday I've told this talk will be English. But today I prepared just in maybe in Chinese. And but so forgive me if I'm not fully prepared. So, and maybe we can firstly saw a video, 2 minutes video about what.
Today we're going to try and break a world record here in terms of proving throughput on a laptop. I'm Eli Ben Sasson, co-founder and CEO at Starkware, and I am joined by Shahal Papini, co-creator of Cairo and co-inventor of CircleStarks cryptography. So Starkware back in 2020 introduced the Stone Prover, which was the first to scale Ethereum with general purpose proofs and has been doing a smashingly good job. But we're building the next generation prover called Stu. So, and we're going to test it now on throughput. Shahal, what are we going to see here?
Okay, so show the screen. Okay, I have the Stu we project out, and I have a test. This test is going to run 64 proofs, each one proving 2 to the 16 Poseidon hashes. Alright, so let's start by running it. Okay, this runs, by the way, Stu is open source, you can check it out today. And this should take a few seconds. Alright, we got it on 6.7 seconds, the entire thing.
6.76 seconds.
Right, okay, and what does it mean? I have this computation here in Python. Like I said, 64 instances, each one has 2 to the 16 hashes, and it took 6.76 seconds, so we got 620,000 hashes proved per second on M3 laptop.
Amazing. So this breaks the world record in terms of proving throughput on a commodity or on a laptop. And I just want to give some context. It is roughly 1,000 times faster than the first generation Stone Prover. And it is the highest recorded proving throughput on a laptop. This is an M3 Pro, a beefy machine, but still a laptop. And what does this mean? Well, when Stu reaches production, which is slated for early 2025, so in like 6 months or so, you can expect to see much higher throughput and to be able to prove on the likes of this laptop the kind of throughput needed to run Visa scale TPS. Stay tuned.
Cool. I think it's pretty amazing when I heard the word about 620,000 per second hashes, right? Because in the early, when we test the other system, proving system, it's already amazing when it reaches the 1,000 level TPS, right? But it's even faster when we use the CircleStarks things. So today I will give you a kind of brief overview about CircleStarks, which is we will take the bottom-up approach. Vitalik is here. He wrote a post also about CircleStarks months ago, but I think he's take the top-down approach, right? So, and by the way, I think I will introduce our group, or maybe it's a new name, it's a new group. It's called zkpunk. I think it's it's an invisible group in the invisible garden, right? It's so because yeah, cool. And this is a artist QR code about the zkpunk.pro website, so you can scan it. I think it's already cool itself because the QR code itself is a coding scheme, and the error correction ability of it is based on the Reed-Solomon code, right? So it's also used in the Fry scheme, and the CircleStarks also is a generation of the Reed-Solomon encoding scheme. And you can also scan this. This is also a QR code, right? If I need to tell you. But it's all Circle. It's also encoded a URL about a website which I call Awesome CircleStarks, which is a repository to organize some awesome materials about the CircleStarks related when you want to learn these kind of things. And you can ask me if how to reach it when I finished. Oh, I think I missed a disclaimer, maybe. But yeah, I'm not a very expert, especially in this CircleStarks. Especially, I don't have one deep understanding background of the algebraic geometry, right? That thing is a very mathematical foundation of the CircleStarks. So I think in this kind of aspect, I'm also a learner with you. The good news is we have a kind of a week ago, a week ahead, so we can discuss and learn it together. So basically, the CircleStarks, when we take from the bottom to the up, it can divide it into these layers of. I draw it in the circle way because it's circle, right? So the core of it is everyone knows it's a unit circle. This algebraic data structure can be used to be a group, which just like the elliptic curve. When we take elliptic curve over a finite field, we can form an elliptic curve group, which means we have a group option in it. So based on the circle group, we can extend it, encode some polynomials in a larger space, which we call a circle code. It's just like the Reed-Solomon code I mentioned earlier, because it's when we encode some information in polynomial and encode it in a circle code, the code word, we will have ability of the error correcting, right? So based on this circle code. But circle code is actually a generalization of the Reed-Solomon code. It's not directly within the, I think, the polynomial ring, univariate polynomial ring, but it's the element inside it is inside the space name is called I think it's called Riemann-Roch space, whatever it is, but just a name. And building on this, we can have maybe the main ingredient of the CircleStark, which is Circle FFT and CircleFly. So, and we can add some maybe arithmetician steps on the top, and we got the overall of the CircleStark. So this is the tech stack, and we will divide it into maybe these 4 parts. So circle group. Sorry for the unclear of the graph because I have limited time to prepare. So in the regular Stark, which I means the Stark we used today, like in the Stark wires repo, like in the risk zeros, and maybe polygons Plankett race, and just a univariate is also called a univariate Stark, and we can see it is actually over a one-dimensional line, right? We can to drop off the zero, and which is the multiplicative group of the over the finite field, right? But when we use it to do an FFT, we need this group to be P -1 smooth, which means we have a very large power of 2 subgroup to do the FFTs. So because we can say maybe in the baby bear, we have P equals to, forgive me, some minus 27. Okay, cool. Yeah, but it's maybe Goldilocks. Goldilocks is also a small field. I think it's 64 and minus 32. Okay, cool. But both of them, when we -1, right, we will have a large subgroup of this over the power of 2. I think it's 50. Oh yeah. Okay. That's what's that? -1. Maybe fun. But anyway, it has a very large subgroup, which we can do very quick FFT on it. This is the same. But when we want to do arithmetic in something called M31, which M stands for Mersenne prime, which is 2 to the 21 minus 1. Yeah, but this group do not have this property called P -1 smooth, right? Because when we P -1, we can only have a factor of 2, right? 2 is not large, has a large exponent over it, right? But there's a other line of work called EC-Stark. EC stands for elliptic curve, so it's just use very complex math to extend the regular Stark into the elliptic curve group, which means we will introduce some geometry structure to do the cryptographic things. So this is a equation of the elliptic curve, And the polynomials, this is univariate polynomials, right? And this is actually not a polynomial, but a rational function. Yeah, a rational function in some bivariate. I think it's also Riemann-Roch space, right? Yeah. So I think the M31 group over M30, a circle group over the M31 field, which is used in the CircleStarks things. And I draw it by some Python code. So this is the blue point is the M3 circle group. When we say M3, it's just like M3, which means this exponent is 3, which means it's 7, right? So, and we can say if we take the equation as a circle, which means it's x squared plus y squared is equals to 1 mod this p, which is 7. We can say why it is distributed like this. Like if you substitute, I say x equals to 2, maybe we can say it x equals 2. So y squared is equals to what? 4?
Yeah.
Oh. So y, the first y is 2. The first y is minus 2, which is 5, right? So we have these 2 points, which is 2, 2, and 2, 5. So another interesting thing is how many blue points in this group? 1, 2, 3, 4, 8, right? So we have a group which has 8, which is p plus 1 group. P is 7, p plus 1 point group, which is called p plus 1 smooth group. And we can use this group to get over this issue about two do not have a large exponent. So this is I draw when we take the M3 to the M17. We can say it's actually very beautiful because it has, firstly, it still has some circle structure, even if it's over the finite field. And secondly, I think compared to the elliptic curve group, which only have one axis of symmetry, I think this group maybe have four axes of symmetry. I think this degree of freedom by the axis of symmetry is I think it's the source of beauty, kind of source of beauty, right? So if anyone also interested in it, you can put it to draw the really M31 group. When you you need to take some time, but you can also draw it. You can also take some clever tricks to draw make it more accessible to the readers. Like by using the you can only draw the domain, right? You can domain of the evaluation. So why do we want to use this M31 group because engineerily speaking, the 2 to the 31 minus 1 is just 31, it's just 30 ones, right? It's binary representation of it. So when you do some polynomial arithmetic, reduce it, you do not need to do a very expensive division with remainder, right? You just need to do some bitwise AND operation and to plus operation and to some very quickly operations like the redshift. So it's a good group when and the engineer will love it. Actually, it's maybe the performance is like 1.4 quicker than even the small field baby bear. So I think it's promising. So yeah, we introduced it group. It's a curve. Everyone knows it's a curve. When you can think of it as a unit curve, just like over the complex group, not group, complex number system, which is just a complex plane, right? So, which is like, it's everyone are familiar with this one. So we need to define some group options over this group, which means we take one element in the group and another element in the group, which we call 2 points. The multiplication of it, we need to define this group operation. So as the inspiration of the complex plane, we just define the operation as a rotation operation over this unit circle, right? We can take maybe one point over there. The first one is B, with the coordinates of it is cosine x and sine x, and another one may be I think it's just there are some abuse of notation there that you don't think this x and this x, but this points coordinates is cosine x, sine x. So the x is just this how to say the arc, yeah, the arc degree of this thing, and similarly there are another point which we need to additionally rotate by this y degree, right? So the final thing is just the coordinates of the C is just cosine x plus 1 and sine x plus 1. And by the trigonometric function formula you learned in the maybe middle school, right? It's just like this. Cosine, you can think of this just the cosine. X coordinates are cosine and y coordinates are just sine of some arc, right? So we can define this as a group option of our circle group. And the group has 1, 0, which is just this point as a neutral element, which means it always calls identity of the group. And for any point P in this, we call this the circle group. because it's circle group over some finite field. And we shall call this operation as a rotation or translation by P, right? So it's just the same. It's just by the point P. And we will need to define another two very useful operations when we, based on this group operation, when we will need this operation when we do some FFT or fry and things. The first one is a squaring map, right? Squaring map, which is just a point multiplied by itself. Multiplication is defined by this group action. So we can substitute the same point coordinate here. And so we got this. And this, because y squared is equals to 1 minus x squared. So it's also, we got this. This thing is very useful later. And group inverse are given by the degree 1 map, which is very simple. It's just you need to map your points just over the horizontal axiom of symmetry, right? Like in the elliptic curve group, you just take the x coordinates the same and the y coordinates to be the negation of it. So we need to define something we need, the actual domain we need in the circle FFT operation. So the first is called the twin coset. This is just maybe we take a cyclic group Jn minus 1, and the size of it is just 2 to the n minus 1. And we multiplied it by Q, which is just a group action, right? We defined in the last slides. And at the same time, we union some Q minus 1 to multiply the same thing, same J n minus 1. How does it mean? Because we can see it as a picture. I think it's a snapshot from the paper, original paper. It's just a size like this. We maybe as a start we take something like the Jn minus 1 as maybe this line, and we not this line is line cross the circle, right? Which means these 2 points, and we firstly by Q we can like to just rotate it to the 2 right points, and the J minus 1 operation is just take these 2 points to these 2 green points by the same arc degree, right? The interesting thing is each of them are just a reflection from this axiom of symmetry. This is the same, like you take it just a rotation operations, like from this to this and to this, and the upper and the lower bound are just a reflection. So there is some very special condition, which is called the standard position coset, which is also a twin coset. Again, it's a coset of the twin coset itself is a coset of the subgroup Jn, which like which means just like in the upper three circle, you can see it's evenly divided by the in the circle, right? And this one, they just has some the symmetry from this axiom, but they are not actually evenly divided in the circle. So the upper three are just, as they say, it's called the standard position coset, which is a special case of the more general condition is a twin coset. And there's some important lemma, which said if D is a twin coset of N, then its image pi D, pi is just a squaring map. Under the squaring map pi, the image of it is a twin coset of size N over 2, which means the squaring map can half the size of the twin coset exactly by 2, which means we can use it as a very useful tool when we do circle FFT, because we need a 2-to-1 map, like a group endomorphism in the FFT domain selection process. Cool, and I think this just a very interesting math, because this lemma here says this isomorphism, which means it's one-to-one correspondence between the circle group and the projective line P1 and F over Fp. So what's a projective line? I will not need illustrate it very clear today. Maybe tomorrow or in this week, we will dive into more about the projective geometry and even algebraic geometry. But basically, projective line is just a regular Euclidean line plus something called a point at infinity, which means what they cite here is just isomorphism. We can derive it maybe if we have time, but it's very. I think it's simple. Just it's basically says there's a isomorphism between a circle group. We can draw a circle group as a circle, right? Maybe over the complex plane, maybe. And the equation of it is, of course, x squared plus y squared is equals to 1. And it says, and we can take this point, which is -1, 0, as I think the term is the pole, right? It's a pole. Yeah. The pole of the projective line. So we can draw a line around this pole, maybe like this line. So we can write the line function. Let me see. It's y equals to, I think if we take the slope, the slope as t, as this t. So line equation is just x plus 1, right? Yeah, so it's maybe we can jointly list these two equations, and if you can say the t is just y over x plus 1, and if you just do another way, maybe we can get this one, but I don't think I will list the detail in this room. It's very simple, actually. You can do it as an exercise, right? To just derive it. But there's some subtlety here, because this line, 0t, this line is just parameterized by the t, right? It's the entire y axiom plus something called point at infinity, which means this line is just to rotate around this point to farther, and to something at infinity. So when this line is just parallel from the y-axiom, when at these circumstances, the point of the line reaches its point at infinity, and this point at infinity are just isomorphism with the point at infinity of the curve of the circle curve. So why these coordinates are listed like this? You need to learn something called homogeneous phi, maybe something like that, maybe tomorrow. But don't worry, we don't need we don't need too much projective geometry things to understand the CircleStarks, how it works. So we will, after the encoding, we will live in the space of polynomials. We just listed here as actually our bivariate polynomial pxy is just over some quotient ring f. This f is just the extension of the original f, which is this f, fp, and it's over the equation of the circle group, and the degree of p is bounded by the n over 2. And we can do something like the Reed-Solomon code called circle code in this space of polynomials, which just evaluates this polynomial at some evaluation domain D. We take the results of it as the set of the circle code. I think it's called the code word. It's also called, I think it's also a linear code, right? Because it's also a generalization of the Reed-Solomon code. I think if you are familiar with the original phi, when you are familiar with the Planck, right? You will need already familiar with the concept of vanishing polynomial. It's just a polynomial vanished over some domain you want, right? Like in the univariate setting, it's just not this one, but it's just to some multiplication of some linear term over the evaluation domain, right? it's very similar over there, but the only difference is just in this polynomial space in the previous slides. So the general form of the vanishing polynomial is like this, because you need to consider the points pk and qk. And what we mostly care about is vanishing polynomial over the FFT domain. So in this special circumstances, when we take the squaring map n-1 times, and we will finally map the domain D to this xd and plus and negation yd point, right? So the vanishing polynomial is just to reduce to this formation. I think you need to drop off the 0 points. The point is you need to evaluate to 0, right, over this vanishing polynomial when you take some point in D, right? So this one is and you take the x coordinates of this, the result of this, so you will get xd, and so we need to minus xd, and you will get the 0. Actually, the actual formula of the vanishing polynomial is even simpler, and note that whenever D is used as a standard position call set, which is a special case of the twin call set, and the image is again a standard position call set, thus xd is equals to 0. In this case, the vanishing polynomial Vd is Vn itself. So we can, vanishing polynomial, the first 4 terms of it is just like the x squared minus 1, and you substitute this x2 to the x squared minus 1, and 2 you can read it. It's clear. So finally, we got into the CircleFT thing. It's used in some efficient encoding and some polynomial arithmetic, as every FFT does. Like in any kind of variant of the FFT, you need like this structure of the chain of domains, right? And the relation between these two domains, where you will need a mapping, maybe 2-to-1 mapping, to maybe you can instantiate it into many things like the group endomorphism things. And this mapping is called the Twiddle factor, and it's used to, I don't know what it's used to, but we also, in the CircleFT, we also need to build such a kind of chain of chain maps of the domain. So we just take this path. This path is actually very simple, because this mapping is to map the Dn to the quotient group Dn over J. J, as if you remember, it's just take the y coordinate as a negation, right? So this group just don't invariant over the how to say this operation. symmetric operation, and another this pi mapping are just a squaring map we talked earlier, which can, using the lemma released earlier, it can exactly half the domain size of each step. So if we take dn as 2 to the n, and finally we'll got some trivial elements as a base case, right? So in the first step, it's just like the regular FFT. You can, if you got a bivariate function, you will divide it as the even part and the odd part, and the even part and odd part is respectively calculated by these things. And later we will get an example. You can see how it works. And in the other steps, and we will receive some function from the previous step. We also call this function as f, and as a regular FFT, we can divide it as 2 parts. But this time, if you remember in the regular FFT, this pi x part is just like x squared, something like that, right? And but over there, our squaring map pi x is 2x squared minus 1, which is just the x coordinates of the squaring map, right? So you can see here is when at this line of the chain of the domain, we already only care about the x coordinates. So where's the y coordinates? Y coordinates are just mapped to cancel out. Maybe in this, you can say this f0 and y5 is already a univariate polynomial. So this is a theorem called the above algorithm will output the coefficient ck with respect to the FFT basis, which is listed in the next slides, maybe, so that we can linear combination of the coefficient ck and this basis, FFT basis bk, and we will got the evaluation to f over d. There is a proof, but it's complex in the original paper. But you can remember this theorem. So the FFT basis is just how is it? If we take j between this interval, and we got the bit representation of the j, and as j0 to the j minus 1, and you can represent the FFT basis of as this Bn of polynomials, which each of them are as this form. And this term is corresponds to the first mapping, right? And V1 and V to the n, Vn minus 1 is the vanishing polynomial of the standard position. So each of this term are corresponding to the other steps of the FFT domain, mapping of the domain. Maybe when we take the n equals to 2, we can calculate this basis as this term, because this each of the terms are linear independent. So it actually indeed forms a basis of what? Of just FFT space. If FFT space is just a subspace of the polynomial space we talked earlier. But I think it's a string compared to the multiplicative basis or the Lagrange basis we're already familiar with. But I think it's interesting. Oh, there's some Circle FFT code in Python. Do you know who wrote this code? Okay, it's just a Vitalik Futri wrote. Yeah, in the GitHub, I think. I think it's clear because very clear, like the we just set the two cases about y and don't care about y cases to divide the conquer of the domain. Maybe you can try to run it by yourself. I think it's very good and clear. So the inverse FFT is just the inverse of the formula to reconstruct the other, to do the FFT in the other side. We can take, it's not very clear, so we can draw it here because it's a very simple example to demonstrate the FFT, circle FFT. So firstly, we got a okay, we got a circle. Oh, that's bad. Sorry. But maybe you can evenly divide it by 8 points because it's a standard position call set over this group. Oh my God. Why is this? Not good? Oh, sorry. But you got the idea because I think it's why this one is maybe in here. And the point is we have this circle and the coordinates of this domain point is just like in this one is A, B. And by the symmetry of the group structure, we got this one as minus A, B, like, and this one as BA, and so on. And we need to do something like the interpolation. No, not interpolation, it's the charges. Interpolation, yeah. It's the interpolation of some varied polynomial over this domain. Like in this point, AB, we got 1, 2, 3, 5. You can say it's a Fibonacci series, right? It's just a Fibonacci series. And we need to reconstruct the bivariate polynomial by the interpolation operation, right? So how to do it? Yeah. Maybe you forgot the formula. We can see it here. Like how can we construct the f0x? We take the fxy and the fx minus y, the 2 points, maybe this 2 points, to add them up and divide it by 2, which is 4, right? Something like that. Is
7.
okay. Okay. 4, 5, 7, like 11. Yeah. And similarly, and I will not list here. You can subtract 3 by 5, which is -2, and divide by 2, which is -1, right? And similarly, this is +1, and these are similar. 2 minus 8 divided by 2, which is -3, and +3, -6, +6, -10, +10. And we can illustrate the f0 and f1 separately by the values over there. And why there are some denominators over there? Because in the original formula, it will divide it by the y coordinate, right? So like in this one, it's -10, but as the formula says, it will divide by y, and the y coordinate of the this one is 8, right? So f1 is something like this, and as we say, the f0, there are some symmetry over there, so we can just to represent the group by the half of the domain point. But at the same time, there shouldn't be any ambiguity when we only take care about the x coordinate, right? You can compare this one and this one. So we still evenly divided the group structure by this to represent the f0x. Similarly, f1x. And the second decomposition step, which we take the f0 as the input, and we will divide it as 2 parts, and the mapping is 2x2 minus 1. So, and this is the formula. And similarly, we also connected this 2 as a pair, and we do some calculation according to this formula, like 5 plus 7 divided by 2, which is this. Is that right? 5, no, it's 6. Yeah, it's 6. And 4 plus 11 divided by 2, which is 15/2. And similarly with the f01, but you will note as the formula size is divided by x. So these are, I think there are some typos over here if you notice because this a should be over the denominator, right? Because we will divide it by this coordinate. Over there, this is right. Yeah, over there, the a should be just down in the denominator. And again, we will have our third decomposition. We take the F000 again to divided it as two part, even part and odd part, and we finally got to F00x, and again in the third decomposition, the F00x will be divided into something which is a constant term. Right, it's the base case. So if we take them back and expand the decomposition from the scratch, so we will get the fxy into after the first decomposition as two parts, second decomposition as 4 parts, because each part will divide it to 2 parts, and 8 parts, and another double the terms. And we substitute our values, we will got our final representation of our polynomials over the this FFT basis, right? So that's the FFT. And I will很快了。Oh, you got this? Okay. So, like the CircleFry is just very similar as the Circle FFT. If you understand Circle FFT, CircleFry is just to replace the recursively divided process as something called the random linear combination step. Similarly, you will just in the folding process of the fry, and you need to take the random linear combination of the 2 parts of the challenge, and how this random challenge is from the verifier, and to draw from a large, this F is an extension of the original F, so it's a larger group, and we can, it's very similar from the original fry, right? It also has a Curie phase to check the consistency of the formula, the oracles, the response of the oracles. So we also can have batch CircleFry when we take this lambda 0 as a parameter of the random linear combination to similarly commit a batch of functions to prove the proximity of this code word from this generalization of the Reed-Solomon code space, which is circle code, right? So, and the full CircleStark around the CircleFry, when we take some computation, we take some trace domain, right? We represent our computation as some trace domain H, and the trace domain is a standard position call set of the circle group. And the trace is organized column-wise, and each placed over the domain in the usual manner, and using the group translation T by the generator of T for the timeline as a air arithmetization method. And the trace columns, which is the witness data, are interpolated by polynomials, but in this time it's over this polynomial space, right? And these polynomials are subject to a set of constraints, like Euro, which means this constraint pi. It's about some selector polynomial Si and each different polynomials, and the polynomials combine some t, which is a rotation operation over it. So the general formulation of the polynomial is like this. And so the constraint, we need to ensure each part of the constraint is equal to 0. And the polynomials are committed by their values over a larger evaluation domain called D. D is a standard partition call set at least double size of the H. This step is very similar with LDE, which means low degree extension step in the regular Fry, I think. So the D is a larger group. Maybe we will take some call set of it to separate the evaluation domain. So I just listed the final circle IOP for the air arithmetician method. And when we doing this circle IOP, and we can maybe take some Fred-Shamir to make it non-interactive, and we finally will get the final version, non-interactive version of the CircleStark. So the circle IOP is the interactive version of it. So the prover set up the domain evaluation oracles for the this P1 and PW over D and send them to the verifier. After receiving a randomness from the verifier, the prover computes the domain quotient, which is called Q beta, satisfying this identity. The beta is used to combine each of the constraints into one, right? We can check the linear combination by beta of them to is the quotient, domain quotient is QB, and VH is just the vanishing polynomial over H as 0. And it sends the oracles this for their values over D and lambda to the verifier. The overall identity to be proven is just they are same, and VH and Q beta will be expanded over there. I think there are some thing called dimension gap over there, and which I need to explore it further. The verifier then samples a random deep query, which is a random point out of the domain, which is a technique introduced by the paper called deep Fry, right? Draw a uniform from the circle curve over the extension field and send it to the prover. And the prover answers with the evaluation claims, like this one for the weighting polynomial and this one for the segment polynomial. And both the prover and verifier engage in a batch circle Fry protocol, which I listed just a few slides before, for the real and imagined part of the deep quotient. This deep quotient, like very similar in the deep Fry technique in the original universe case. For each, and which is I think a joint proximity test to the circle code where n is equals to H. If circle Fry passes and the evaluation claim satisfies the overall identity at this point, so the verifier will accept, otherwise it will reject. I think, okay, thanks, CircleStarks. No, yeah. Oh, cool.
Yeah, thanks for the session. For me, to be honest, some of the math I wasn't fully able to follow, but I think that's fine for me. For me, it was maybe the goal to get like intuition
Yeah, cool.
So from my perspective now, just to clarify, like the CircleStark essentially uses the kind of the properties of more like the M31, like the cyclic nature of the modular field.
Yeah.
So have more efficient operations than we previously had, so we can actually have a faster proving time. So that's basically from my intuition, just kind of like if I were to like put the entire session as an outcome for me. Is that true, or is that?
I think it's true. I also have a very similar feeling of you. It's just use the structure of the circle, and maybe there are some deep math over there.
Yeah, sure.
Yeah.
I think the biggest efficiency is basically that the M31 field is just really easy to compute over because you don't actually have to do a modulus. You can just compute everything with shifts.
Yeah. Yeah.
Yeah, thank you.
Cool. Yeah.
So the challenges from the very higher output in the extension field, right?
Yeah.
The actual,
Right. What?
the extension field.
Yeah. It's
All
must.
the challenges from the very
Yeah. All the challenge must. It must from the extension field, because the base field we won't use the small. Oh, I erase it. But we won't use the small field, right? If we just take the welfare challenger from the base field, I think it's not large enough space to be secure, right? So I think you must draw it from some larger extension field.
But if FRI, the verifier need to send many coefficients to make all the many polynomials into only one, so the coefficient is in the finite field or in the extension field.
Because the parameters, which is the challenge value is from the extension field. I think the result, it will reside in the extension field either. Cool. Okay, anyone?
Yeah. So actually, I'm a little bit lost for the left corner picture.
This one?
Yeah.
Oh, yeah,
So
cool.
from the EC curve, sorry for the ECC.
ECC?
The group element was on the curve, right? So, but for this picture, I'm a little bit confusing because like 0t is not on the curve, so.
I think what it says is this isomorphism between this circle to some line. Right. This line, and I think.
So in an implementation, the only place where any of this actually matters is when you actually have to choose a random challenge point. Because the way that you choose the random challenge point is you just like choose a random value and then you use the projective equation and turn it into a circle point. Like aside from that piece, you don't actually have to care about projective like anything at all.
Okay, that's a good news. And what? Maybe in the tomorrow and in this week we can dive into some more details of it, if you are interested. Thank you， 谢谢大家。
About this week, we have our master Wang Yao. He will talk about the math.
Hello, everybody. I'm going to be your math teacher tomorrow.
Cool math.
And I'm going to talk about some math basis about CircleStarks. So let me. Do we have? So as you can see, Kurt talked about all these circle groups and these points. And tomorrow I'm going to go through all these computations and provide a solid math foundation for what does it mean by you have a single group, how it is a group, and like including the projective geometry. So the rule, as a lot of people might not know, that the rule, the maths behind Snark and Stark, these things are based on projectile geometry, also elliptic curves, projective variety. I know all these things sound buzzwords for you, but let's go through these things tomorrow, and we may find some pleasure about playing with this math, so you can have more of a feeling about these things. Okay.
Cool.
Yeah,
So tomorrow it will be 2 p.m. at upstairs, and wish all the people who are interested will come. Thank you.
and finish today. Thank you.
I learned the class.